Now for part 5. Welcome, this is side A, side B. In this video, we got something extra, ladies and gentlemen. In fact, we've already gotten more than what we originally thought, because we thought we could cover this series in about 3 videos. Were we ever wrong? What's coming up in the short term, following up with the proof of the division property of exponents for rational numbers. To clarify though, e to the x is actually well defined for all real number exponents. In our last video, we finished the proof that e to the x is injective by stating the exponents a and b are real numbers. If that's fine with you, the proof is done. However, ladies and gentlemen, what if that's unacceptable? So, for our channel and yours' interest, we're about to do a study. The division property of exponents holds for all real numbers, which includes rational and irrational numbers. So instead of accepting the status quo at face value, so to speak, rather the following study is meant to seek a deeper understanding.
Well, I think you ought to tell the truth.
I went to the beach this summer and I watched the waves. Now, a wave is a wave, but only for a second, and then it's over. But the water that makes the wave continues to exist. It's just not a wave anymore.
That's a lovely thought.
Thank you.
To prove rational numbers, we need supporting proofs. First off, a discussion of the nth root definition for exponents, sometimes called the kth root, spelled Q-T-H, which states the nth root of a number x is a number r such that r to the n equals x. In the expression nth root of a number x, the root is the number r. When multiplied by itself n times equals x. N, the index or degree of the root, indicates how many times the root number must be multiplied by itself. For example, if r equals 2, we have 2 times 2 times 2, the number 2 multiplies itself, n equals 3 times, which equals the number 8. So by the nth root definition, we can simplify the expression as 2 raised to the power of 3 equals 8. And that's that. We're just simplifying notation. As a result, requires no proof, because we're just rewriting a well-defined multiplication operation. What naturally follows, the nth root of x, which is r equals x, raised to the power of 1 over n. What's going on, folks? We believe 2 things are happening. First, the nth root applied its own definition to itself by raising both sides to the power of 1 over n. And then using the power rule for exponents identified as the green square allows n times 1 over n just equals the exponent 1. The operation returns label 2, which is r equals x to the 1 over n. So label 1 applied its own definition to itself to get label 2. Secondly, there's another way of defining label 1, but here, label 1 is defined by its inverse, label 2. It sounds strange, but that's what's going on. Because, just consider the following, which actually goes great with the current topic of inverse function. Getting back to the topic, right? To find the inverse of r to the n, which equals x, we replace x with r to get the first orange bullet. Then we raise both sides with 1 over n. Then use the power rule that returns label 2. Observe, label 1 used its own definition to find its own inverse. Take a look, the beige box. Label 1 is also defined by its inverse, label 2. But if we want to find the inverse of r to 1 over n, just apply the definition again. Perform the same operation, but this time raise each side to the power of n. Returns back to label 1, the original definition. The inverse, an undoing operation. That being said, the nth root of x is just a number x raised to the power of 1 over n, whereas the nth root of a number x is a number r raised to the power of n. It's really strange because The process between label 1 and its inverse implies we could have began with label 2 as the original definition. What do you think? Okay, enough is enough. Going back to the previous example, raise each side to the power of 1 over 3 returns the blue box. 2 equals 8 to 1 over 3. So in the context of label 2, the nth root of the number 8 is itself raised to the power of 1 over 3. For the sake of clarity, and our channel is not on a deadline, we want to show notation equivalence. The blue box is label 1. The radical and rational exponent notation are the orange and yellow boxes respectively. The radical notation is read as the nth root of x. The yellow box is the nth root of x, labeled 2. We want to show both are synonymous. The power of a power rule for exponents is the green box, which is, if a power is raised to a power, we can just multiply them as a product. We'll use all of them to show equivalence, the white box, but more a demonstration than a formal proof. The statement in the white box defines the fractional exponent notation to mean the same thing as the radical notation. It provides two different ways of writing the same mathematical expression. In short, x to the 1 over n is the same symbol for the nth root of x, which is represented by the notation in the orange box. For the most part, that's 100% acceptable, but let's go further. But if we're going further, to be clear though, in the context of the principal root. Next blackboard, please. No, not a root vegetable as a principal. Yes, that's something very relevant to the current study. The principal root for a positive real number x is the unique positive square root, which is represented by the radical symbol. For example, 16 has two square roots, positive 4 and negative 4. The principal square root is positive 4. The principal nth root is equal to x to the 1 over n. From the last example, the principal square root for 16 is positive 4 if n equals 2. So the principal nth root, x to the 1 over n, results in a unique positive number k. But that should look familiar, as it just implies label 2, the nth root of x. If we let e be the base and x the variable, we can do a rewrite in the blue box, which is read as e to the 1 over n. But do you see any problems? Because if it can't be resolved, there's no sense to carry on with this study, ladies and gentlemen. Here's the facts. In the blue box, it's been established we aren't considering the negative nth root. However, e to the x is defined for negative exponents, such that we get the red box read as e to the negative x. But there's a problem. The blue box is not considering the negative. However, the red box considers negative exponents. But we can resolve it, since we can write e to the negative x as 1 over e to the x. Observe, the exponent in the denominator is positive. Very nice. Because in the last bullet, we can write the blue box for negative exponents as e raised to the power of negative sign, brackets, with the term 1 over n inside the brackets, which just equals 1 over e raised to the 1 over n. Voila! Observe the denominator again. The exponent is positive, so the notation of the gold box resolves the blue and red boxes. We can happily move on. In column 1, we start the demonstration by letting r equal x to the 1 over n, which is the yellow box. Then we raise each side to the power of n. We can apply the green box to the right-hand side. In column 2, returns the blue box. Since we have label 1, by definition r is the nth root of x, and through the entire process, which satisfies both the orange and yellow boxes. Therefore, x to the 1 over n equals the nth root of x. This is because raising a number to the power of 1 over n is the same as taking the nth root of that number, concluding the notation equivalence, also demonstrating a fundamental relationship between roots and exponents. Well, we hope we did, because we had to center our logic in one direction, Because the definition seems to be always on the move, like water. Because the nth root can be defined by itself and its inverse. Therefore, its inverse could be the nth root of a number x. It goes this way, but also goes that way. It applies its own definition to itself to come up with another way of defining itself. It's like turning your shirt inside out. It's a different shirt, but it's the same shirt.